Throughout history, great civilizations have built monumental infrastructure, roads, canals, railways, and highways that reshaped the world. Could the next great engineering project be a superhighway to space? A space elevator could revolutionize access to orbit, but like all grand infrastructure projects, its success depends on two key factors: materials and economics. A few months ago, we explored space elevators, the improvements in their designs, and the challenges that remain. We concluded that the prospects are improving, as we now have non-microscopic quantities of materials strong enough to make one feasible. However, many obstacles still stand in the way, and we didn't get to cover them all. That episode ran nearly an hour long, and even then, we only scratched the surface of certain topics. Two key areas that deserved more attention were the economics of space elevators, how they would be funded, built, and operated, and a deeper dive into material options. Today we'll focus on the economics and practical uses of a space elevator, and next month we'll take a deep dive in the materials that can make it possible. And of course, if you'd like to be notified when that and other episodes come out, be sure to like and subscribe. The economics of building a space elevator. There are essentially 5 phases to space elevator economics, and right now we are still in Phase 1, basic groundwork and theory. Soon we'll move into Phase 2, R&D and basic prototyping, as our ability to mass-produce graphene, graphene superlaminate (GSL), carbon nanotubes (CNTs), and other ultra-strong materials continues to improve. And it is improving, but we'll save the specifics of that for the materials episode. Phase 2 would likely conclude with real-world stress testing, such as stretching a prototype tether several kilometers long horizontally under great force to check for unexpected behavior. Suspending tethers from high-altitude balloons anchored to the ground to observe how weather and wind conditions affect them. While modeling is valuable, real-world data is critical. These first 2 phases are unlikely to be particularly expensive, but they also offer no profit, only investment and expenditure, though you might have other areas of related investment prosper, as graphene research would likely find a strong market in airplane wings, car hoods, and many other areas that would fuel research that would benefit space elevator development. Phase 3, launching a prototype, is where things get more serious and potentially where the first revenue might emerge. At this stage, we will be primarily testing climbers on a small-scale elevator. We might also see early commercial interest. Even with higher risks compared to rockets, some companies may be willing to pay for cargo transport. Space elevators are vastly cheaper to run than a rocket, at least for climber cost. We'll get to other costs soon, but it makes sense to run your tests with climbers carrying a load, and there's a lot of satellites or fuel that might benefit from climbing up on a system where the primary cost is launch, not construction. Companies may be happy to take that risk. However, we must be realistic about the risks. We should assume at least a 50-50 chance that the first prototype will experience a critical failure. Rockets were hardly new technology when SpaceX got started, for instance, and yet the majority of their early rockets blew up or otherwise failed, which is part of the reason early space launch prototypes, from rockets to mass drivers, tend to be focused on carrying cargo, not people. In fact, this early phase of space elevator development doesn't even plan on carrying humans. It's entirely focused on cargo, testing, and redundancy building before we consider passenger transport, and risk losing people. This early space elevator does not go down, not because it cannot, but because a single tether can only be used one way at a time, and each trip takes a week or 2, though faster ones may be developed later. There's not much demand for bringing people down from space, though amusingly I'm writing this just after SpaceX launched a rescue mission on Pi Day to retrieve our stranded astronauts. Cargo return is not a priority either. If needed, we could bring cargo down via the elevator, but it is far simpler to send re-entry capable pods up, assemble them in orbit, and let them return to Earth naturally. Even when we have dozens of elevators in operation, we'll likely still only have one dedicated to bringing people back, and maybe a second for redundancy, given that it takes a week or 2 to retask a tether with traffic moving up it. For the most part, our climbers only go up, and we'll use them as building materials once they reach the top. As a reminder, large stations positioned at or above geostationary orbit serve as counterweights and hubs for space travel. Every time we add another tether, strand, or ribbon to the elevator, we also need to increase the station's mass or extend the upper portion of the tether. This extra mass can be used to whip ships out into deep space, toward the Moon, Lagrange points, Mars, the asteroid belt, or anywhere else in the solar system, all at a fraction of the cost of launching from low orbit, let alone from Earth. Phase 4. Early Operations. At this stage, we've moved beyond the prototype phase and into full-scale operations, though we are still refining and improving the system. This is also when we begin to see a major shift from rockets to space elevators for cargo transport. With multiple elevators in operation, prices start to drop, but strategically. It is worth noting that rocket costs are generally given as the cost to LEO, low Earth orbit, while space elevators go to GEO or beyond, which is far more expensive for a rocket. Early on, the cost per kilogram is cheaper than rockets, but not by much. After all, why charge only $10 per kilogram to break even when rockets are still charging $1,000 per kilogram? Instead, you might charge $500 per kilogram, making a 5,000% profit while still massively undercutting rocketry, and allowing for more and bigger elevators to be paid for. There are only 3 reasons you would drop prices further. 1. Government subsidies. A government, corporation, or coalition funds lower pricing to accelerate space expansion. 2. Competition. Another company builds a competing space elevator, forcing you to adjust prices. 3. Market expansion. Lowering prices attracts more business, increasing total revenue. For example, if you can make $1 billion in annual profit by charging $100 per kilogram and moving 11 million kilograms to space, that's far better than making only 500 million by moving just 1 million kilograms at a higher price. We could also see regulation or government pressure to lower prices too, though I would guess a desire for more traffic would be the main force. Let's not forget, the people willing to invest in a space elevator in the first place are likely to be strong advocates of space expansion. They might even accept lower short-term profits to drive long-term growth in space infrastructure, and whoever owns that tether factory wants to keep churning out space elevators too. Phase 5. Late-generation technology and operations. This phase focuses on advanced space elevator technology and large-scale operations, which is not our main concern today. However, we will revisit it later to discuss topics such as non-equatorial elevators, the mass transit of millions or even billions of tons of cargo and people per day, and off-world applications like tethers to Lagrange points or space elevators on other planets. The key idea here is that a carbon-based tether tens of thousands of miles long could likely be produced for less than the cost of just a few miles of highway. Carbon is cheap, and nothing about producing graphene or carbon nanotubes, CNTs, is inherently expensive or requires rare materials. Boron nitride, on the other hand, could be a different story, but we'll cover that in the materials episode. Even optimistically, a space elevator can probably only lift a mass similar to that of the tether itself, so it won't have the throughput of a highway. The baseline 12,000 layer thick ribbon we discussed in our last space elevator episode is designed to carry 7 20-ton climbers and mass around 1,000 tons. So even if we assumed we could manufacture that at more or less the cost of the carbon feedstock, say graphite, that would still run $1 million. Right now that production cost would be vastly higher, but we might imagine it getting to the low millions for such a tether down the road. In the nearer term, a tether capable of carrying a dozen 50-ton climbers at once could cost less than $1 billion to manufacture and launch into space. If we assume such a tether operates for more than a decade before needing replacement or equivalent maintenance, its cost per kilogram becomes remarkably low. For example, if it lifts 50 metric tons, 50,000 kilograms per day, for 4,000 days, about 11 years, that's 200,000 metric tons, or 200 million kilograms transported. Such a tether would mass around 2 to 3 million kilograms, and the feedstock is only a few bucks a kilogram, so we could imagine that tether costing $10 million to make, and maybe $10 million more to carry up another space elevator, but let's go with $1 billion for the moment. Even that might be optimistic for tether number 1. At that scale, the cost per kilogram taken to orbit would be around $5 per kilogram, and just 10 cents if that lower $20 million figure ever became possible, That's more or less our high and low end estimates though, and we should certainly assume the high end early on. Of course, power costs would be higher, likely several dollars per kilogram based on current energy prices, but by the time we reach this stage, space elevators will have made access to geostationary orbit so affordable that large-scale space-based solar power is almost certain to be in place. At that point, terawatts of solar energy harvested in orbit could make power on Earth vastly cheaper, and energy costs for vehicles in space even lower. In fact, we might not even need beam power anymore. We could be running electricity directly down space elevator tethers instead. We also need to consider other operational costs, but by this stage, a ticket to orbit might cost about the same as a transcontinental or transatlantic flight, and we would likely be living in a world where GDP per capita and median income are significantly higher than today. Early operations. We'll revisit Phase 5 later, but for now, our focus is on Phases 3 and 4, where space elevators move from prototypes to early operations. In the space elevator episode from late last year, we discussed a prototype climber and tether design. While its selection is semi-arbitrary, the default model proposed by the International Space Elevator Consortium, ISEC, features a 20-ton climber, a ribbon-shaped tether, a material as thin and translucent as saran wrap, and a width similar to a roll of gift wrap. In this system, one climber is launched per day, with multiple climbers ascending at once. Given how we traditionally think about space launches, it's easy to assume this would require a massive facility, but in reality the setup is surprisingly modest. The most practical approach is likely a large ship stationed along the equator, serving as the deployment and support base for the elevator system. This does not require a custom-built vessel either. While a helipad might be useful, the only essential requirements are the ability to onboard cargo in the 10-ton range, a below-deck area for handling and preparing cargo for transport, and sufficient mass to anchor the tether against wind and other forces. That last means that generally these ships can't afford a lot of space for cargo, operations, guests, and so on, as they do need to be decently big. Though a powerful engine and fast-reacting computer could let you get away with smaller ones, maybe even the large yacht size range. In theory, you could limit cargo size to under 1,000 pounds or even what a person could carry, allowing the climber to be loaded manually while hanging rather than requiring the ship to support its full weight. But you do need a certain amount of mass to keep the tether from yanking the ship around. There's a lot of perturbing forces in play, from our planet not being a perfect sphere to it having wind and weather, so a big container ship or an old nuclear-powered aircraft carrier might both be ideal, though probably anything the same general mass range as that tether, which we expect to be in the low thousands of tons, ought to be sufficient. It might need to be big enough to push back on the air drag a meter-long ribbon passing through several kilometers of atmosphere might exert, and for instance a 1-meter-wide tether experiencing a 40-mile-per-hour wind on say 10 kilometers of height, or 10,000 square meters of surface area, will experience 440,000 pounds of force, the equivalent of 220 tons. You'd obviously have a problem if your ship engine wasn't designed to move that much mass. For context, a modern US aircraft carrier is generally around 100,000 tons, and container ships can be much smaller or much larger than that. For my part, I like the idea of a tether that might retract above the atmosphere in bad weather and drop to let someone's personal yacht, or even personal spacecraft, attach to it, but that's definitely not an early or mid-term scenario. That said, considering the scale of operations and other costs involved, a medium-large ship would be more practical. A refurbished feeder-class container ship, even on the smaller end of that category, would offer sufficient storage for weeks' worth of cargo awaiting launch, onboard equipment for loading, maintenance, and climber storage, crew quarters and operational space, and the cost. A used feeder-class container ship runs just a few $1,000,000 at most, far less than the aircraft carrier-sized operation some might imagine. At this early, low-capacity stage of space elevator deployment, you do not need a Panamax-class freighter or aircraft carrier or anything remotely that large, just a well-equipped mid-sized ship to serve as a stable, mobile base. That's the last item we can assign a specific price to, as we simply don't know what a tether will cost to produce. Until Starship becomes fully operational and reaches mainline production, we also can't estimate how large of a tether we could deploy in the first launch, or what the cost per kilogram for that launch would be. We also haven't settled on an exact design for climbers, as we're still determining the best climbing method, As we discussed before, space elevator tethers are not only hyper-strong, but also extremely slippery, similar to ice. This makes climbing them difficult and prevents easy attachment methods like gripping mechanisms or drilled pins, especially since the material is so incredibly sharp it could slice a steel pin in half under a twist or shear. People often ask whether a tether could be sabotaged, for example by cutting it. That is certainly possible, but if you swung a sword at a tether ribbon, you would slice it in half. The sword, not the tether. Now we have good reason to think we can get the coefficient of friction up to something more like 0.6, more akin to pushing a brick across a table, which would solve the problem. That's a topic we'll explore further in our deep dive on space elevator materials, but this is one of those challenges where real-world testing is essential. You need large quantities of the material in production before you can properly evaluate design options. No one doubts that we can build a working climber, but we can't finalize the design until we understand how it interacts with the tether. The various climbing mechanisms must be tested on the actual material first. Current adaptations of the 20-ton climber design suggest a cargo capacity between 10 and 14 tons. If we were to replace that with passengers, additional mass would be needed for life support, accommodations, food, water, air, and radiation shielding, since the journey would take 1 to 2 weeks. Faster climbers would likely be developed over time, as reducing the travel duration would cut down the mass needed for life support and crew supplies. While it's speculative at this stage, the trade-off between speed and added hardware would likely favor faster climbers once the technology matures. For example, the SpaceX Dragon capsule has a dry mass of 12.5 metric tons and can carry 4 to 7 crew members, so suggesting a 20-ton climber could accommodate a similar number of passengers is not an overambitious idea. That said, passenger climbers would likely be larger and more comfortable, whereas the 20-ton version is primarily designed for cargo, especially in the early days when its main role would be hauling up additional and larger tethers. But this design should still be capable of carrying people if needed. The challenge comes when it's time to bring them back home. Unless you increase the return capacity, you would need one of these 3 solutions. 1. Modify a climber for re-entry, allowing it to safely return to Earth. 2. Assemble re-entry pods at the terminus station, so passengers can return in separate vehicles. 3. Dedicate a climber line for descending passengers, or clear the existing line periodically to allow return trips. To be fair, we could also imagine a more flexible system where climbers can detach from the tether, thrust away for a few minutes, then reconnect, allowing multiple cars to pass each other. Considering we can now catch rockets with chopsticks, this is not the most extreme engineering challenge ever imagined. Climber economics: reuse versus repurposing. From an economic standpoint, the key issue isn't whether climbers can be reused, but how they can be repurposed. They are not expected to be highly complex, but then again, neither was a rocket, until we started building them. These climbers might end up being a significant cost factor in the system. Given that an empty climber weighs 6 to 10 tons, you could run 2 or 3 times as many down on a dedicated return line as you send up on the primary ascent line, but whether that's viable depends on how expensive climbers are to manufacture. One alternative is to salvage and repurpose their components once they reach orbit. Their material and hardware could be valuable for space construction, not just as cheap radiation shielding or raw building materials, but as high-value components for ongoing projects. You might strip out expensive, low-mass parts and send them back to Earth for reuse, but odds are virtually all of the mass and components would find a hungry market awaiting them up in space. Nonetheless, you do need some sort of return option. For example, the space elevator might not run every single day. If we assumed it was offline for maintenance a few weeks per year, you could collect all high-value components, load them into 1 or 2 climbers, and send them back down just after the last inbound climber arrived. A lot depends on how much demand there is in space for climber components versus their cost of production on Earth. If we ballpark the cost of a climber at $1 million, which is likely on the high end, and assume a payload capacity of 10 tons, the low end, then the per kilogram cost of discarding a climber after each use would be $100 per kilogram. You might recoup some of that cost by reselling components, but even with resale, this pushes the cost toward the edge of economic feasibility, especially considering other operating costs. And personally, I tend to think Starship will hit its launch cost targets, or at least come close enough to remain competitive. On the other hand, if we assume a more reasonable cost of $100,000 per climber carrying a 14-ton payload, the price drops to just $7 per kilogram. And at that rate, you could turn a profit just selling the scrap, especially if it's usable for something like radiation shielding in space. The actual cost could end up higher than $1 million or lower than $100,000, but somewhere within that range, a balance will emerge between reuse, resale, and recycling. If you are regularly moving people and their luggage down the elevator, it makes sense to send valuable cargo back down as well. Of course, any sending cargo must be worth more than the opportunity cost of sending additional mass up, so what qualifies as worth it will vary. That price point will likely shift over time as production scales and space infrastructure expands. And there's always the hybrid approach: strip out the low-mass, high-value components for return via climber or re-entry pod, and leave the rest to be used or repurposed in orbit. Expanding the elevator network. My hunch is that once the first tether is operational, it wouldn't be long before it spawns sibling and cousin elevators, with at least one dedicated downline. Indeed, the first cargo of a space elevator might well be another one, or the components of one. You can thicken and add capacity to a tether by simply running some more tether in parallel, even skinnier ones that the tether can't carry the entire weight of an additional tether. And if one mass is 1,000 tons and a climber can only carry 20 tons, this implies you are assembling tethers in space, or using many smaller ones to bundle together. Keeping tight clusters of tethers together without collisions is a challenge, but if that proves infeasible, we could simply space them out. In theory, we could have thousands of ships, each with its own tether, spaced just a kilometer or so apart, covering every available section of the equatorial ocean. You could also have the actual cargo pod of the climber suspended on short tethers that extend out like legs to grasp many tethers at some distance, with a foot that climbed each. Tethers do not precisely have to be at the equator either, so do not think a long line of tethers right on the equator, all in parallel. Many might be miles off it. There's nothing inherently expensive about the tether, ground station, or counterweight station. So, once a single tether is operational, we are likely to see a major surge in space launches. Not every nation will want one, but every country with a space program likely will, and you can bet the major space powers will want multiple. After that first tether, the cost of setting up another could drop to $1 billion or less, maybe way less, depending on how expensive tethers are to manufacture at that point. Yes, a tether might just be carbon, but so is diamond, and this isn't just raw coal, but ultra-high precision manufactured carbon. That first tether will likely weigh 1,000 tons, possibly more. Given the advantages of microgravity for material manufacturing, we might even haul coal or graphite into orbit to manufacture tethers in space, which would remove the issue of sending one up on a rocket or a climber, or trying to join thin tethers or shorter segments. But it wouldn't take long before we started sourcing carbon from off-world, using asteroid mining or lunar resources. While a space elevator is ideal for reaching geostationary orbit, GEO, or heading off toward interplanetary destinations, rockets will still have a vital role to play. Peter Swan, one of the experts from the International Space Elevator Consortium who helped edit this script, calls this the dual space architecture. Space elevators are not well suited for reaching low Earth orbit, LEO, because most of the tether stress comes from the portion that passes through Earth's atmosphere and low orbital regions. As climbers ascend, gravity weakens, allowing the system to handle more mass the higher up it goes. That's why rockets will likely remain a good method for reaching LEO. You could drag a payload a few hundred kilometers up the tether and detach it to fire into orbit, which saves some fuel and reduces high-speed atmospheric stresses, but not enough to make rockets obsolete. Dropping payloads from higher altitudes and relying on atmospheric skipping or air braking to settle into a low Earth trajectory is plausible, but frankly, I wince at the prospect. We may also see skyhooks and rotovators take on that role, particularly for transferring payloads from high orbits to low, but for more on those options, check out our skyhooks and rotovators episode from a few months back. You also might use space elevator tethers to hang a mass driver from, so that its muzzle exited over the atmosphere, which might be a good approach to cheap LEO launches. A proven and reliable rocket system will still have plenty of customers for a long time, especially for quick deployments, LEO launches, and specialized missions, A space elevator complements rockets, but does not replace them. What space elevators do is allow us to move enormous amounts of mass beyond low Earth orbit, LEO. Any module small enough to fit into a climber or easily assembled from multiple transported pieces can now be sent to geostationary orbit, GEO, or even higher altitudes at a fraction of traditional launch costs. Once you're beyond medium Earth orbit, MEO, the fuel required to achieve stable circular or eccentric orbits, such as a Molniya orbit, drops significantly. Additionally, the engineering challenges of spacecraft construction also decrease, since slow-burning a rocket engine in the vacuum of space is far simpler and less stressful on materials than surviving atmospheric exit and re-entry. We tend to estimate operational costs for a space elevator at around $10 per kilogram. It could end up higher or lower, but I like using round numbers for discussion, especially given the uncertainty in all these projections. Plus, these episodes get watched for years and inflation tweaks the numbers anyway. Capital costs and amortization could increase that figure significantly, but even in the most pessimistic scenarios, a space elevator's cost structure still competes with the most optimistic estimates for Starship's cost to GEO. That said, a space elevator is not primarily for reaching geostationary orbit, though many satellites, solar power farms, manufacturing hubs, and fuel depots would benefit from deployment there. Even if geostationary transport was all the elevator did, it would still likely result in every G20 nation, and many others, having their own station positioned above some stretch of their country's longitude, essentially just hanging there, and most probably within a decade of that first elevator, and either lots of privately owned ones or people renting out space from that counterweight station, or other nations' own stations. Moving between stations in the geostationary ring requires very little fuel, and if enough stations existed, they could be connected into our ring with tethers, not even requiring super strong materials. Such a system could serve as a transport network for people, cargo, and power between geostationary platforms, and critically, this could be built in a way that allows stations to bypass unfriendly ones. On Earth's equator or over it at GEO, it is a thin band, not a one-dimensional ring, preventing any one country or entity from monopolizing or bottlenecking movement in geostationary orbit. In fact, you can extend very long arms or tethers north and south from GEO, so long as they are attached and counterbalanced to something at GEO or the opposite side. Beyond GEO, space elevators as interplanetary boosters. A space elevator's primary purpose isn't just reaching GEO, that's the icing on the cake. The tether doesn't stop at the counterweight station. In fact, a counterweight isn't even strictly necessary if the tether extends far enough beyond GEO. It will counter itself. The key is maintaining balance, with mass above the geostationary orbit pulling up to counter the mass below GEO pulling down. This works because at a 24-hour rotation, anything beyond GEO moves faster than needed to stay in orbit at that altitude, creating tension that keeps the system stable. If the tether extends beyond GEO, the speed at which objects move along it increases. At twice GEO distance, you're moving twice as fast around the Earth, 4 miles per second, 6 kilometers per second, instead of 2 miles per second, 3 kilometers per second at GEO. But the orbital velocity there is only 1.4 miles per second, 2.2 kilometers per second, meaning you get free delta V just by releasing from that point. That already sets you on a good transfer speed to the Moon, or even better, to the terminus of a lunar space elevator, likely positioned at the lunar L1 Lagrange point. Since a lunar elevator can be built from aluminum rather than exotic materials, we can assume one has been deployed, probably extending down to the lunar South Pole. After all, elevators do not have to be equatorial. Even a modest extension past GEO, requiring no additional engineering challenges, saves massive amounts of fuel for operations in cislunar space and around the Earth-Moon Lagrange points. At 3 times GEO distance, your orbital velocity drops to 1.2 miles per second or 1.19 kilometers per second, but your actual speed along the tether increases to 5.7 miles per second, 9.2 kilometers per second. Now that's a free delta V of 4.5 miles per second, 7.3 kilometers per second, enough to reach interplanetary transfer speeds exceeding basic Hohmann transfers. You might need fuel to go even faster, and you still need onboard fuel to fine-tune your trajectory and rendezvous with your destination, whether it's a planet, Jovian moon, or asteroid mine. But by fueling at the counterweight station, which likely stores large amounts of propellant as part of its mass, you have not burned any fuel yet from your onboard tanks, a huge advantage for deep space missions. At this point, ion drives become an excellent option. While they provide low thrust, their high efficiency makes them useless for escaping planetary gravity, but perfect for interplanetary travel, where time is abundant and solar power is plentiful. Additionally, those larger solar power collectors we discussed building at Geo could serve a dual purpose, beaming power to departing or arriving ships, either boosting ion drives or providing direct radiant pressure for propulsion, powering electromagnetic catapults that could launch spare fuel pods to spacecraft, reducing the need for onboard fuel storage. For more on this concept, check out our Mass Driver vs. Rockets episode from earlier this year, where we explored the potential of mass driver-based launch systems. And again, I expect we'll see a wide array of launch and propulsion systems in the future, just as we still use rockets, planes, and trains alongside cars, bikes, and even good old-fashioned walking. Before we get back to the nuts and bolts of megastructures and why they might be a good investment, let me pitch you on something just as wild, but a bit wetter. Imagine launching into space in a starship that's basically a glorified aquarium. It's not a sci-fi fever dream, it's a serious concept, and we dive deep into it in Fishbowl Starships, our latest monthly exclusive. The idea? Use water, yes, the same stuff you shower with, as radiation shielding, impact armor, thermal control, and even reaction mass, because if you're crossing the void at high speed, it turns out a giant tank of H2O might just save your life. You can catch Fishbowl Starships only on Nebula, the creator-owned platform where I release all my episodes early, ad-free, and occasionally aquatically. You'll also find brilliant deep dives of other crazy-sounding engineering projects like our space elevator, such as Real Engineering's look at the insane engineering of the F-117 Nighthawk, just some of the great content on Nebula in addition to this channel. Want to support the channel and never worry about another renewal again? Nebula now offers lifetime memberships, $300 one time and you're set forever. Or go with the annual plan, just $36 a year, cheaper than a tank of gas and probably safer in deep space. Head over to go.nebula.tv/IsaacArthur and see how we're turning speculative science into spectacular storytelling. And trust me, this ship is watertight. Why space elevators change everything. The key takeaway is that once space elevators are in play, they drive down the cost of everything we do in space. They allow ships to reach Mars faster and at a lower cost, which in turn reduces the need for heavy radiation shielding, since shorter trips means less exposure, and even that shielding becomes cheaper to transport, making deep space missions more viable and scalable. This cost reduction scales everything up. The cheaper space access becomes, the more we can build, explore, and expand. That's one of the most powerful aspects of space elevators. Starship is an incredible system, and I fully expect SpaceX will make it work, but it won't single-handedly create a Star Trek style or space opera future, where most people visit space at least once in their lives, and many work or even live there. This isn't just about cost or even the environmental concerns of using vast amounts of fuel. Yes, we could make fuel more sustainably with space-based solar power, electrolyzing water into hydrogen and oxygen, or even producing carbon-neutral methane and hydrocarbons from carbon dioxide and water using excess energy from space-based power stations or abundant nuclear fission or fusion. But ultimately, true large-scale space expansion requires infrastructure that scales, and space elevators can scale. While we can't really have several thousand large rocket launches a day, we could have several thousand space elevators operating along the equator, each with far higher capacity than the 20-ton climbers we discussed for early operations. As mentioned, early tethers would be as thin as yarn or as wide as a roll of gift wrap, but capacity scales linearly with cross-section. For example, a circular tether 100 times wider has a cross-section 10,000 times larger, allowing it to carry 10,000 times more cargo, say 200,000 tons per climber. At that point, we're in freight train territory, and yet the tether itself would still be no wider than a modest tree trunk. Space elevators are quiet, low energy, and generate minimal waste heat, a key advantage, especially when considering far future Kardashev-scale civilizations, where waste heat management becomes a major bottleneck. Indeed, a K1 civilization, a planet-wide city or ecumenopolis, might find it more energy efficient in terms of waste heat on Earth to grow food in space and bring it down by tether. Speaking of big cities, this lack of rocket blast also means elevators can be located within cities. While equatorial locations are ideal, non-equatorial elevators are possible by having tethers from opposite hemispheres converge at a shared counterweight station. This adds significant weight to an already mass-constrained system, but if feasible, it would lead to direct urban space access. Non-equatorial space elevators and urban integration. If non-equatorial elevators become practical, we could see them in use for many reasons: extending directly from major cities rather than remote equatorial launch sites, operating from boats in coastal harbors, allowing flexible placement, generating less noise than a train and likely being much quieter, avoiding the need to cut through cities since they ascend nearly straight up, with a less steep angle the farther they are from the equator. Not too sharp an angle even at higher latitude though, as being a few thousand miles north or south is fairly small compared to 22,000 miles distance to Geo, and would be an angle of just 8 degrees off directly up. So it won't interfere with city operations, but a skyscraper-based space elevator terminal isn't out of the question either. Even a tether capable of lifting an entire freight train would still be thinner than a telephone pole, making it far less intrusive than cell towers or airplanes cluttering the skyline. To maintain stability, you'll likely need a winching system to keep the tether taut. As we discussed before, if tethers turn out to be highly sensitive to weather, they may need to be disconnected and reeled up to the lower atmosphere, which at just 1% of the total tether length wouldn't be a major operational challenge. But that same winching reeling system could allow us to experiment with direct orbital tethers, extending from space all the way to the Lagrange points or lunar elevator stations. With further advancements, we could even develop longer tethers capable of delivering high interplanetary speeds for outbound missions. For more concepts along these lines, check out our Interplanetary Infrastructure episode, where we explore how space elevators and their cousin systems, the orbital ring and rotavators, could evolve into even larger-scale transportation networks. For now, the potential of space elevators is exciting enough. Imagine leaving directly from any city for a trip to high orbit, a journey that might take a week initially, but with improvements could be reduced to under a day, and all for less than the cost of an overseas flight. More importantly, this could mean affordable trips to the moon and back for not much more. This is exactly the kind of technology that snowballs quickly. Once a space elevator is operational, I'd expect that within a couple of decades, a person could afford a trip to the moon. And once the materials are ready, which could happen within this decade, a topic we'll discuss next month, we could see space elevators popping up worldwide within the decade that follows. By the late 21st century, it's entirely possible that couples will be taking honeymoons at counterweight station hotels or even on the moon. With or without space elevators, the slow crawl to space is speeding up to a sprint, but if we can make them work, that sprint will become an avalanche, one that inexorably takes us up, not down, into a bright new future.